We have seen friction before where the force of friction was less than or equal to the coefficient of friction times the normal force, but this is a different situation where drag is actually related to how fast the object is going. Let's dive in. Drag is a frictional force that happens to exist in a fluid. Primarily, we will be considering air resistance. It can either vary with speed linearly or quadratically. Let's say that this little guy has just jumped out of a helicopter that's hovering some distance above the ground. There's a force of gravity that's pulling him downward toward the earth, and with his parachute open, he has a very significant upward resistive force, and that resistive force depends on how fast he's moving. Let's consider that initial condition where he's first stepped out of the plane. In that case, the velocity would be 0, and so the net force acting on him would simply be mg. Let's consider then the case where he's moving at such a speed that he cannot get any faster. That's terminal velocity. And in that case, mg is equal to kv upward. So the terminal velocity vt, rearranging that equation, is equal to mg over k. If you're looking at a case where it's somewhere in between those two limiting cases, then the net force would equal mg downward minus kv upward, or ma equals mg minus kv. This is a unique situation where acceleration is the derivative of velocity, and they're both in the same equation. That's called a differential equation. What we ultimately want to do is find velocity as a function of time. So the words that we're going to use are, we're going to say we have a first order linear differential equation that we're solving. It's first order because it's using a first derivative. Acceleration is dv dt. It's linear because the force, remember, was related to kv, not like kv squared or kv to the third or something else. It's differential because it involves velocity and acceleration, which is velocity's derivative. So what we'll do is we'll separate variables and integrate both sides in order to solve for velocity as a function of time. Starting with Newton's second law, where we said that the mass times acceleration, as this person is skydiving and falling out of a plane, is equal to the downward force of gravity minus the resistive force of the air. And the acceleration is the first derivative of velocity with respect to time. So we have this equation. And what we're going to need to do is we'll separate variables, we'll do some substitution to make it a little bit easier, that kind of a thing. Remember that we had said that for the case of terminal velocity, that the sum of the forces actually was then equal to 0, and so that means that that downward force of gravity is equal to the resistive force. And so what that means is that the terminal velocity, so when it's no longer speeding up but still falling, is equal to mg over k. And I'm going to end up substituting that in here. So I almost have that here with this mg, but if I divide by k, then I would actually have vt, and it would also get rid of this k, which is hanging out in front of velocity, which I don't want. So let's divide everything by k, both sides of the equation. So that's m over k dv dt is equal to mg over k minus v. And now I can substitute vt in there. So m over k dv dt is equal to vt, that's the terminal velocity, which is a constant value, minus the velocity. Keep in mind, we're looking for velocity as a function of time. So I'm going to need to rearrange these things. I need to get the v's on one side together, and I need to get everything else on the other side, and I need to separate that derivative statement. So I'm going to take this piece here and divide it to the other side. So that will be 1 over vt minus v. And as I'm separating variables, I'm going to keep the dv on this side and the dt will end up on the other side. And when I divide this to the other side, it will become the reciprocal. So it will become k over m. To find the velocity, I will need to integrate both sides. On the left-hand side, I'll be integrating from 0 to whatever the velocity is after some period of time, which I'm finding on the right-hand side by integrating from 0 to t. So the right-hand side is going to be pretty easy to integrate. I'm going to go ahead and do that real fast. So the integral k over m, remember, is just a constant. So that'll come out front, and I'll be integrating from 0 to t of dt. And that'll become then k over m t evaluated between 0 and t, which means that that's going to become k over m t. Easy peasy. The left-hand side then is going to take a little bit of work. I'm going to need to do a u substitution here. So u is equal to the bottom, which is vt. Remember, terminal velocity is a constant. And I'm going to take the derivative then of that. That's how you do a u substitution. The derivative of a constant is 0, so I'm going to be left with negative 1. That means that du is equal to negative dv, or that dv is equal to negative du. So I can go back into this integral that I had up here. This is going to become the integral from 0 to v still, but we'll put the u substitution back in. This will be 1 over u. Don't forget this negative. It has to come in here. So negative 1 over u du. And you might remember from calculus class that the integral of 1 over u is the natural log. So we'll end up with a negative, don't lose track of it, it's still there, negative natural log of u evaluated between 0 and v. Oh, okay, let's put those things back in. So before we had said that u, we had said, was equal to vt minus v. So I'm going to plug that back in, vt minus v, and we're going to evaluate this between 0 and v. So this is going to become negative natural log of vt minus the velocity that I'm looking for, minus, oh bother, there's a lot of negatives in here, negative natural log of vt minus, in this case, it'll just become 0. Okay, we have actually evaluated the left-hand side of that equation that we had up here. I'm going to put these two things back together. Remember, I was just simply finding the integral of the left-hand side. So these two things are equal to one another. So I'm going to have a negative natural log of vt minus v minus a negative natural log. You know what, just for fun, why don't we go ahead and make that a positive? So positive natural log of vt, remember minus 0 is just itself, and then that's equal to k over mt. So again, I'm looking for v, and if you remember your rules for natural logs, this would become like natural log of vt over vt minus v. There's nothing wrong with doing that. The only thing is that I'm solving for this. And so I actually want to flip it and have that v up on the top. So I'm going to move the negative to the other side right now. So in other words, I'm going to divide both sides of this equation by a negative 1. So this is going to become a positive, this is going to become a negative, and this is a negative. And so now I'm going to keep going with the natural log rules. So in other words, you put a subtraction together into a division. So this is going to become natural log of vt minus v over vt. Some of you might be thinking that didn't make any difference. It does. It just makes a step now instead of later. And on the right-hand side, we would still have this negative k over mt. Now, I keep reminding myself, what am I looking for? I'm looking for v. I want to get that alone. That's my job here, is to find velocity as a function of time. So I need to exponentiate both sides. So e to the natural log is going to kill it. And e to the on the right-hand side to that mess is still going to be e to that mess. So this is going to become vt minus v over vt is equal to e to the negative k over m times t. Oh, we're getting close here. So vt, this is now just algebra, minus v equals vt e to the negative k over m t, and I need to subtract vt from both sides, so I'll have a vt e to the minus k over mt minus vt, but I don't want negative v, so I need to multiply a negative 1 through to the other side. So that'll become a negative vt e to the negative k over m t plus vt. And I'm going to go ahead and factor out a vt from there and just make it prettier by putting the positive in the front. So I'm going to have vt times 1 minus e to the negative k over m t. And that is velocity as a function of time. But wait, remember, we had substituted vt ages ago. Up here, we had said that, remember, a terminal velocity was defined as mg over k. So let's go ahead and put that back in because we have those values. So our final formula is going to be vt, velocity as a function of time, is equal to mg over k times 1 minus e to the negative k over m t, and that is a wrap. Now, some of you are saying, oh, I could look that up on the internet and that would give me a formula. Yes, you sure can. I have also seen many years where they ask you to derive this formula on the AP test. So it is what it is. It is probably worth your while to know how to do it.